Okay, I think we'll go ahead and get started so we stay on time. So this morning was focused, I guess not entirely, but a lot on differential privacy, on robustness. The talks going forward are going to be a little bit different. So I'm going to be discussing synthetic data generation in the context of a missing data problem. And then we'll have two other speakers with other applications of synthetic data generation, and then we'll finish with a panel. So what I want to talk about in this presentation is an approach, or actually I guess I should say it's an ensemble of approaches to synthesize data for completing power grid network graph models or graph databases for resilience modeling. And this is work that I'm doing in my capacity with a team at One Concern. This is a firm about 5 or 6 years old, uses a variety of machine intelligence, different kinds of machine learning on fairly large, messy data sets to do resilience modeling. So this is trying to model resilience of commercial property and eventually residential property to large catastrophic events. So that's the problem domain. And then there's some joint research also with some universities, UC Berkeley, which I'm affiliated with, and also with the University of Michigan. So there's a number of people that are involved in this. And what I'm going to do in this presentation is try to zero in on one part of this modeling exercise, which is actually quite large. So I'm going to touch on a few of the others just to provide context. But I did want to start with an example. So this is really the motivation for why we're even doing this particular application. So this was an earthquake in 1994. It's called the Northridge earthquake in Southern California, and happens to be one of the most damaging earthquakes just in terms of property damage, which that's what we're specifically focused on. So when you have the event, what happens to the property has happened down in Los Angeles. And one of the things that is interesting when you look at these events is that it's not just the direct damage to the building that you have to worry about. I mean, obviously that's a big issue. So if I have a factory and the factory gets impacted, or I have a warehouse, or I've got a retail establishment, all of these things are a concern if I have direct damage to the building, because obviously it's not used. But what we're trying to do here is we're trying to take this resilience concept to a higher level of resolution and think not just about the building itself, but also what is that building dependent on to create value. And that's what we call these dependent lifeline networks. You know, power is the most important one, because if you don't have power, then most processes in the buildings, maybe, I guess even if you want to have a meeting with your colleagues, you still need light. Maybe if it's in the day and you're with your colleagues, that's probably the only situation you don't necessarily need power. But most of the applications, you do need power. There's other lifelines, which I'm not going to go into, but we're also modeling these dependency risks, such as the transportation architecture, which includes roads, bridges, ports, and airports, as well as the community. So we want to look at a certain radius around a building to understand the impact on the community. Now this gives you an idea of the scale of the problem. So in the United States, there's about 45,000 substations. So these, I'll get into this in a little bit, but if you look at the way power grids are set up, you've got the generation capacity, whatever that is, and then that pushes power over lines to circuits, and then the circuits distribute out to substations, and then the substations distribute the power out to the building. And what we want to do is we want to look at the dependency on each of these 45,000 substations for any given building in the data set. And just to give you an idea, right now we're modeling something like 15 million commercial properties in the United States. So it's fairly large data set. You know, I've done a lot of risk modeling over my career, and I used to think big data was, actually in graduate school I thought big data was 40 data points. That shows you how old I am. Then in my dissertation, I thought 1 million data points was a big data problem. Now we're talking, if you take, each building has about 1 million data points associated with it. So now we're up to the trillions. So we're really getting to a high level of data. Now resilience in this particular context is really the capability to withstand and recover from disasters, as well as learn from those disasters to strengthen future response and recovery. So this is a very specific definition related to property. And you know, it's interesting, this has all of a sudden become a hot topic, but this exposure to physical risk, and I just mentioned this because those of you who are doing research in any adjacent areas, I'd love to have you get more involved in this, because there's not enough people looking at this problem. And investors, insurance companies, asset managers, everybody's now looking at this, at what I would call the missing piece of what's called the sustainability investment approach. There's something in finance called ESG. It stands for environment, social, governance. Typically, environment talks about the carbon emission footprint of whatever activities you're involved in. Social tends to be around diversity and, you know, whether you're using certain types of labor, such as slave labor, and those problems. And governance is how the building is governed, or how the company is governed, either. We're trying to add resilience to this picture because physical risk is a big deal. And unfortunately, it's even a bigger issue in the United States because the infrastructure has not been maintained. And so the question of physical resilience is coming up more often, particularly in light of climate change. So all these things are converging to create this perfect storm of interest in this area. So I'm going to talk about just the overall methodology, just to contextualize the synthetic data generation. I'll talk a bit about these dependent lifeline networks. And then, you know, the focus of this particular presentation is the synthetic infrastructure data generation for power distribution specifically. I should mention that's not the only place we're using synthetic data generation, but that's the one I'm going to talk about here. So just a few terms, because I'll probably slip into these, and if you're not in the insurance or risk domain, it might be new. We typically distinguish a hazard from a peril. So a hazard would be something like a hurricane or an earthquake, and that essentially drives the intensity of the statistical processes or the data generation processes that we're trying to model. But the peril is the thing that actually causes the damage. So for example, if I have a hurricane or a typhoon, it's actually flood inundation that causes the damage. So that would be an example of a peril. Another peril might be wind. So I might have excessive wind speeds, or I might have storm surges on the coast. For earthquakes, typically shaking ground, but also tsunami is another peril. And if I can come up with these models, now this is quite new, so this is a new area, the ability to quantify in a very consistent, comparable way, the resilience gives us the ability to then resilience adjust valuation and risk models. And so that's something that we're attempting to do. And we do this by estimating first fragility functions, and I guess I didn't put it on the slides, but also recovery functions. So the fragility functions tell us what's the different probabilities associated with certain types of damage events. And then recovery is related, obviously, to how to get things up and running. So our objective is to estimate an exceedance probability. So this is the probability that the event or the peril is so bad that the building is not used for some threshold. And we usually set that threshold at half a business day, but it can be whatever you want. And that can be out to different time horizons into the future. So I could look at this at 1 year, or 20 years, 30 years, depending on my application. And then I'm going to calculate a conditional downtime statistic. So conditional on exceeding the threshold, what's the downtime? And that is measured right now in days. And then I can do all kinds of interesting conditioning. So I can condition on different kinds of hazards, which would then include a number of perils. I can condition on climate scenarios. And the point of this presentation is I can condition on the the different dependency, the dependent networks, the valuable operation of the building is dependent upon. So that's the objective then for this modeling exercise. And ultimately, I want to build the foundation for estimating portfolio effects and constructing benchmarks. So that's why it needs to be quantifiable. Now, at a high level, we're going to look at damage ratios associated with the building. So that's still part of this modeling exercise. But there's actually lots of researchers, there's a number of open source tools, and there's a variety of firms that do this kind of work. We do it as well. But it's this piece that I think is the innovation for what we're doing, is understanding the downtime associated with problems or disruptions in these dependent lifeline networks. And so the general approach is to essentially start with the intensity. So the hazard intensity is going to parameterize the model, and then I'm going to look specifically at the impact of different perils. And that's going to lead me to my damage model, which could be direct damage to the building, or the damage to the dependent lifeline. I'm also going to have recovery curves associated with those particular events, and then that will give me some notion of the downtime. So this is the calculation process workflow that we're actually using, and I'm going to concentrate on this the dependency piece, like where we need to use the synthetic data. Now, the model is actually currently sold in two ways. One is called Domino, which is a very structured product that allows you to look into the data, and then DNA is data and analytics. But this gives you a difference between what's typically done for conventional models, where you only have hundreds of data points, and what we're trying to do, which is millions of data points, because we're trying to look at all these dependent layers. I'm not really going to go through this whole structure, but this gives you some idea of where we're applying what I would call machine intelligence. So for example, in this particular slide, I've got logistic regression up here. This could actually be replaced with other things. I could use random forests. There are other approaches that we've looked at. I mention this only because in this specific application, I have to worry about scalability. I have to worry about diagnosability. There's these other conditions or criteria that are more important than just having a performant model. And that's an important thing to just take away. Because often I'll find new graduate students will say, well, why aren't we using reinforcement learning, for example? It's like, well, yeah, we'd love to use reinforcement learning, but it just doesn't scale very well. It's hard to explain to the client. So you have to take into that picture a little more nuance with respect to how you're choosing the model. So then, just to make sure that you understand the context, as I'm going to get into the details next, and sometimes you lose the forest for the trees, but we're taking multiple data sets, and I guess I should mention that the data that we're training on is a mix of data, vendor available data, open source data, and also data that we collect. So sometimes we'll actually go out to damage sites after a big event like an earthquake or a typhoon and collect ground truth data. Then, this is an important point for this particular workshop, is the synthetically generated data, because the ground truth data is messy, it's often not available for certain locations, and so it's trying to address that issue that we're synthetically generating the data. From there, we're going to estimate our target variables, either direct damage, and actually there's a training step in the middle there. So we're going to actually train in the context of that larger algorithmic loop, and that's going to give us the exceedance probabilities and the conditional downtime, and the ability to incorporate climate scenarios into this picture. So let me now talk about dependent lifeline networks. So if we think about what makes a building valuable, or I guess you could also say this about your home, it's the different infrastructure systems that provide lifelines. So obviously power, but also water, telecommunications, gas and liquid fuels, transportations. And the characteristics of these particular components are that they're often geographically distributed in a wide area. They are an interlinkage of lots of different specialized components, and that'll become very relevant for power. And they're interdependent, and there's a variety of subsystems. Now, one of the things that I'll just mention quickly here, and this is part of the reason why we're very interested in synthetic data generation for privacy preservation, a lot of this data is quite sensitive. So you can imagine if I have all the detailed data for a particular metropolitan area at this high level of resolution, that actually could be quite useful for adversarial attacks. And so we have to be quite careful, one, on how we use this data, and this is true often for many data sets that we receive. But not all municipalities, not all governments are comfortable sharing data. And so one of the things that we are trying to figure out is how can we create a confidential compute pipeline that in fact accounts for this differential privacy so that we can access more data. That would give us more ground truth data, and we wouldn't need to rely so much on the synthetically generated data, but we're still in the process of trying to negotiate that. Now the question then for these dependent lifeline networks is how is the interruption to those dependent networks, how is that affecting business value? So these are all the things we're going to talk about. I won't really discuss it in this presentation, but optimal mitigation is actually another machine learning application that we're focused on. Because if I have many, let's say I'm a real estate fund manager and I have thousands of properties across the US, I need to figure out, particularly in light of climate change, how to optimally mitigate the risk from perils. And it's interesting because I've been involved in this risk space for many years, and 10 years ago when you talked about this, particularly in the US, not so much in Europe, people didn't take you seriously. They said, well, that's kind of intellectually interesting, maybe we can have some problems in the future, but we're not too worried about it. But in the last few years, it's amazing how quickly the sentiment has changed. Because now you're having bridges fail. We had a whole condo collapse. There's a number of issues in places like New York and San Francisco where you're starting to see large buildings sinking or moving in ways not expected. And much of this is a function of much higher degrees of precipitation, the interchange of heat waves followed by cold waves. So all these things are actually creating this issue around physical risk, and particularly around these dependent networks. Now, unfortunately, as I mentioned, there's just limited publicly available data, and so that's why we need to think about synthetically generating it. So this, unfortunately, is a little bit complicated, but this is kind of the overview of what we're trying to do. So when we're looking at the network, we start with the building locations, because that's something that we know. So we have the latitude and longitude of the building, and in most cases the address, not always, but typically the lat long is something that's enough for the building. We have some substation location information, but not 100%, and that'll become useful later. Now the road network, we've been able to infer from satellite imagery. So you can, generally speaking, figure out the roadways, where the connections are, and that became quite important because it turns out that a lot of the network properties of the transportation architecture, I can't say this for every country, but at least for the US, and particularly California and Washington State, where we've spent a lot of time doing analysis, the power lines often track the roads. So that's one of the areas where you can infer, when you're synthetically generating power grid information, I can infer that to some extent from the placement of the roads and where we see interconnections. Not entirely, but that's one part of it. Building characteristics also matter a lot. So if I have a large building like a skyscraper, that will have one type of power substation and circuit characterization. If I've got a warehouse, that's going to look different. If I have a bunch of warehouses, that again might look different. And so that can be used for developing a power line type classifier, which I'll come back to later. And all of these pieces then can go into the synthetic generation, which here is labeled as a network impact simulation. But essentially, what you're doing is using these characteristics to then generate the network data. So this is really the synthetic network data. And the actual approach, we've tried a number of them, but the one that turned out to be the most effective, looking across all those criteria, was just classification and regression trees. So I don't have to use super high-tech machine learning. I can use some of these more standard classifiers to come up with the capability. But I'm also going to augment this to some extent with physics-based models. And specifically, when I'm looking at, say, the topography of a particular area, that will tell me something about, say, how a flood is going to come into that area and how that might interact with that power grid network. And this is also something that I'm a big fan of, is using physics-based models or causal inference as a start, and then combining that with some kind of machine learning or machine intelligence. I think we just get better models. In this space, I can tell you unsupervised learning doesn't work well at all. Just trying to do deep learning doesn't really work. There's some types of boosting approaches that give you slightly better performance, but you start having some explanatory issues. And so it's important to understand that when you're doing an actual application, you have to really, it's this heuristic trade-off of all these different constraints. That then gives me the ability to generate a simulation based on this network, which then can go into my recovery curves, and I can ultimately, because I didn't put it on this, but I've got the fragilities up here, so I've got the fragility functions, and then I've got the recovery functions. That's going to ultimately give me the downtime. So let me now move to the discussion of the actual synthetic data generation. So what we're trying to do, again, just to remind us of the objective, is estimate at a high resolution the probability of outage and then the estimated downtime, but it needs to be generalizable and it needs to be scalable. And we've got these problems that network data is often not available, that the component fragility and recovery functions can sometimes be hard to estimate. We don't always have as much validation data as we want, and sometimes these models can be very expensive computationally. Now, if we look at the actual power system, this is the level of modeling that we want to do. So we're going to start at the station transformers, because that is actually quite easy to infer, is to figure out where that is. Then, the circuit breakers, I have incomplete data. So that's one area where I've got to synthesize to some extent the data. But as we get to the power poles, the conductors, whether they're overhead or underground, the different switches, et cetera, that's where we start running into trouble with the data. So what we do is we begin with, we put a constraint on the problem. So we assume that the distribution network is going to follow a radial system. And this is actually in line with how engineers think about setting up power networks anyway. Now sometimes they diverge a little bit from these types of plans because of legal reasons or geographical obstacles, et cetera. But this radial system tends to have lower costs. It's on average easier to predict and control. And then the second point is the one I made earlier, which I'll emphasize again, is it depends a lot on street layouts. And so that gives us a lot of training data, so to speak, when trying to figure out where to place these things. Now, I won't go through all of these, but there are other approaches that people have used in the engineering literature to try to model this kind of stuff, whether it be just straight statistical approaches, simulation approaches based on just a physical model, so not necessarily using machine learning, and then certain types of optimization-based models, again, based on physical models. But they all have their pluses and minuses. Generally speaking, they're not very good down at the individual building level of resolution. That's really why we're focused much more on the machine learning aspect of this. Now, the thing that's interesting is we want to link the substations back to the properties, and this is an important component right here. One of the things that we're doing is we're going to infer whether a building can be served by more than one substation. Now, unfortunately, we don't have a lot of ground truth data here. So this is a probabilistic model that goes into the synthetic data generation. So you might know, for example, that substation A feeds this upper green dot, which is one of the customers. But we may then model, and we've tried to validate this when we can, that same customer, if substation A goes down, could be fed by substation B. So we're going to build in a certain degree of probability that arises from the ability to synthetically generate the data. And then that allows us to address the data sparsity in this space. And one of the things, the other thing that we do is we break down this recovery, this fragility and recovery problem into subproblems. So this is just an example that we did on Japan, just to give you an idea of the level of resolution. But here we're going to use the physics-based models to give you some kind of constraint on how we synthetically generate the data. And then we're going to generate the data down at the individual substation point. And just getting back quickly to this graph to remind us, we're going to look at the substation locations, but we're also going to look at the power line types. And I guess I don't have it on this graph, but we're going to look at the circuits as well. So we're going to try to understand all of those pieces in this context. And so this is the actual model breakdown. We're going to first detect what infrastructure we can. Then we're going to essentially identify the service territory geographically and the circuits. And then based on that information, we will, and this all happens after we've actually trained on what data that we have. But we're going to combine that with this constrained model and generate the infrastructure synthetically. And then that allows us to figure out the exceedance probability and the downtime related to the power component of this problem. So this is just an idea of, or this gives you some sense of collecting the data. And it's a mix of data that's publicly available, like U.S. Homeland Infrastructure Foundation, satellite data, allows us to understand like the network effects, and we have some data from data vendors. This gives you some examples of the labeled data for the substations. One of the things that's interesting, I can only speak for California, but we talk to the utility providers fairly regularly, as a matter of course, and we've found substations that they've lost in their data sets. So there have been times where we'll say, oh, there's a couple substations here, we're trying to understand some points, and they'll say, well, we don't see any substations there. That worries me a little bit as a California citizen, that the utility company doesn't always know. But these types of techniques of synthetic data generation can be quite helpful. I'm not going to talk about how it's conventionally done, but as I mentioned, we're going to connect probabilistically to these substations. We're also going to then cluster at the circuit level. Now here, actually I needed to change the slide. It's not technically an unsupervised learning model. This is like a k-mean clustering model that's used to figure out like which substations go to what circuit. So there's kind of there's a hierarchy that's being inferred here and generated. Then we're going to use the building information and the road information to first infer some relationships between the power line types and the things that we're modeling. But then we're going to go back and synthetically generate that for everywhere. You know, there's certain states in the U.S. where there's very little data, so we have to rely on other states. There's certain parts of states where there's a lot of data. So to some extent, the synthetic data generation is smoothing out this data unevenness when we're looking across a large geographic area. This gives you an example on looking at the power line type. So I want to know if it's overhead or underground, because that makes a lot of difference. You know, for example, if I have a flood, it doesn't really affect the overhead as much as it's going to affect the underground. Whereas if I have an earthquake, it may affect the overhead more than the underground. So those are some of the issues we're trying to do. I want to emphasize the fact that we use some computer vision on satellite imagery, but that by itself is not enough. Now, one of the things I should mention is we're talking to a couple of companies that collect data for self-driving car algorithm training, and we think that might be useful. You know, Intel had this subsidiary called Mobileye, so they have cars running around, and they're actually pulling information that can be quite useful in this context. This, I think, is quite exciting in this space, because there's lots of data sources that we haven't even tapped yet, where I think it will be quite useful. This gives you an idea of some of the covariates that can be used to figure out the power line types. And then ultimately, there's an approach which I'm out of time, but called Steiner arborescence, which is it's like an optimized tree construction approach. It turns out you don't quite need to use that, and I'll just end with talking about the model selection. This is on this, please. Ultimately, for each of the nodes in the network, we are going to generate data. So this is synthetic generated data on connecting the shortest path. So it's kind of if you're familiar with Steiner arborescences, this is a heuristic approach to doing a more optimized effort. And I think that's also an important thing to understand in application. Again, the more elegant approach is just computationally very expensive, and I get most of the accuracy that I need using the simple approach. So I'm just really I'm just algorithmically looking for the shortest path, and when I don't have the graph data, which is the edge or the node, then I can just fill it in and complete the network. And ultimately, that's where the synthetic data generation has been very helpful. And then a number of areas where we've done validation. I really don't have time to go into this. I can talk to you offline if you're interested. But you know, we've looked at a number of areas where we actually have quite a bit of ground truth data, and we've tested the methodology on that. And this was all of Southern California. It was about 92.5% accuracy, which at least for us that was pretty good. And so this then gives us the ability to use synthetic data generation to fill in data that we don't have. And I think I will finish there. So just in the interest of time, if you have questions, maybe you can save it for the panel discussion, because we have two more speakers and I kind of want to stay on time to some extent. And I'm also happy to talk with people after the session as well if you have more questions. So thanks for your time on this presentation.